let's say I've got a 0.5 kilogram ball and it's moving this way to the right at 4 meters per second, and it hits another ball that's stationary, okay? And it's an identical ball, 0.5 kilograms, but it's not moving. But after, so this is my before side, after they collide, okay, the first ball was originally moving this way. Let's say that this ball, this stationary ball, let's say it's moving up this way at 30 degrees above horizontal, and the other ball, okay, it's moving this way at 30 degrees below horizontal. Okay, can I figure out what the final speeds of those two has to be? Well, let's think about it. Okay, this is different because it's got momentum in x, and this one has momentum in x and y. So we have to pay attention to our components. So if I want momentum in x, before it's just 0.5 times 4, which is 2 kilogram meters per second. Remember, the stationary ball doesn't contribute anything. Okay, after, that has to be the case. Momentum in x has to equal 2 kilogram meters per second. Momentum in y needs to equal 0. This is not moving up or down, right? X is to the right, y is up. So I've got nothing going on in y. So over here we deal with the same thing. Okay, we can do this. Since the initial momentum in y is 0, the final momentum in y is 0. Okay, these have identical mass, so 0.5 times whatever its velocity in y is, vy, okay, equals, okay, I'm going to go ahead and okay, I'm going to call this one, the top ball, I'm going to call it ball A. So vya equals 0.5 times vyb. Okay, and they're equal because if I subtract this over, it's going to be 0, because this momentum right here has to be equal and opposite to that momentum right there. This would be b. Okay, and so those two cancel each other. So I know that the velocity in y here and the velocity in y here are equal because the masses are equal. So vyb, right, equals vya, and I don't have an exact number for it yet, but I do know they're equal. Also, I do know that the momentum in x, whoops, I don't need a force. Okay, I do know that the momentum in x has to be 2 kilogram meters per second. Okay, so if I'm looking at this ball right here, it's got some momentum in this direction. This ball also has momentum in that direction, and it's equal to vxa times 0.5 plus vxb times 0.5, and that has to add up to 2 because that was our initial momentum in the x direction. So vxa 0.5 plus vxb times 0.5 equals 2, and since these masses are equal, what we end up with is these are going to be identical. But let's just take a look at that. Okay, since vyb equals vya, and okay, these are both similar triangles, right? Since this side equals the other side, these are similar. So basically, vx and vxa and vxb are equal. So I can say vx times 0.5 plus vx times 0.5 equals 2, and so I have half of vx plus half of vx, so vx equals 2. So I know that the velocity in the x direction of each ball is 2 meters per second. Okay, and that makes sense because each one is contributing half the total momentum, and it has to add up to the 2 kilogram meters per second. So 2 times a half is 1 plus 2 times a half is 1. Okay, so they're both moving to the right at 2 meters per second. So now I can actually figure out how fast they're moving in y. I just used my triangle. I know this is 2 meters per second. I know that this is 30 degrees, and I want to know what this side of the triangle is, or if I just wanted the total, I could go with this side. Okay, And actually, let's see, this is a 30, 60, 90, so I would use cosine of 30 equals adjacent over the hypotenuse. So the momentum, or the velocity, I guess since we're in velocity, is just equal to 2 divided by the cosine of 30. Okay? And you would know how fast that ball's going. And it's the same for both because the balls were identical and they did identical things. Now, if they're not identical, it can get a little bit more complex, but just remember, law of conservation of momentum, momentum before and after is the same, and if it's in two dimensions, then deal with x and deal with y, just like we always have before.